So thank you. So we start. We just take a review what we done last time. Uh, Last time we started with a space vector PWM uh, switching technique for two-level inverter, and in that case, initially we discussed the concept of voltage space vector. So three-phase quantity can be represented with a three-phase quantity can be represented with a single vector, and that we can call as single phasor. We can call as a space phasor or space vector. And now we have shown that this is we are taken as the, let us assume that we are already knowing this will be a switching states of two-level inverter. So we are having 8 switching states of the two-level inverter. V1 is 100. It means S1, S6, and S2. Similarly, V2, we are having a V3, V4, V5, V6. These are the 6 active switching states of the inverter. And whereas here we are having 2 inactive states, 000, it means that 4, switch number 4, switch number 2, and switch number 6. Whereas V7 is again a null state, magnitude is 0. It is a 111, S1, S3, and S5 are on. And with that, we have seen that for a 180 degrees mode of conduction, we are getting a space vector at position number 1, 2, 3, 4, 5, like that. Only 6 space vector positions we can obtain in case of a 6-step inverter. Now we want that our space vector should move smoothly. What is benefit if the space vector moves at a uniform speed? What benefit we can get? If this is our space vector, if it moves at a constant speed and a constant magnitude, what will be a benefit at the three-phase output voltage of the inverter? So anybody? Our interest is our space vector should move at a uniform speed. It should not change its steps. It is not the switching of the space vector in steps. It should be a moves as smooth as possible and its magnitude is constant. So what is the benefit if the space vector moves at constant speed with a constant magnitude? It moves at a uniform speed with the constant. What benefit we can get? Anybody? What is the
Output voltage
benefit
will be smooth.
when a
Output
space
will be
vector
smooth.
is having a constant magnitude and it rotates at uniform speed? Then our three-phase output voltages of the inverter are balanced and sinusoidal. So THD in that particularly waveform is very less when our space vector moves at a uniform speed. And here we have seen that in case of 180 degrees mode of this, our space vector is jumping from one place to other place. From V1, it jumps to V2, not moves. Similarly, it stays here for 60 degrees duration or 3.3 milliseconds and then switch to the other. So it jumps. Space vector is jumping from one position to other position. It is not moving at a constant speed. That's why we can get the uh, 180 degrees mode of conduction. We are having the output voltage waveform Cauchy square wave, and because of that we are having almost THD is the 30%, 31%. So that we don't want. Our space vector should move at a uniform speed, so it should move at a very small angle, and that will depend upon the switching frequency. And whenever the space vector is within this hexagon, if you just see the dotted hexagon, this will be a just tip up. If you all tip up space vectors you can connect, then you will get the hexagon. And if it is at the inscribing circle, then we can call it as a linear range. Okay, so here we are having a linear range, and our interest is at this particular position how to apply the V1, how much duration we apply V2. So whenever space vector is in sector 1, we are in 6 sectors marked. So it is a sector 1, 0 degrees to 60, that's sector 1. And when the space vector is in sector 1, the how to get how much duration we apply V1, how much duration we apply V2, how much duration we apply V0 and V7. And that calculation is nothing but generation of the switching signal. So now here, if you see it here, okay, when the space vector is in sector 1, which vectors we can apply, switching vectors. We apply V1, we apply V2, V0, and the V7. And once we have shown it here, this will be a V star. We resolve along V1 and V2. In that magnitudes we can call as a resolve the space vector V star along the V1. That magnitude we can call as VA. Along the V2 we can call as the VB. And based on that, we find out the VA magnitude in terms of particularly V1. Sorry, V star we are knowing, and once V star is resolved, along the V1 is VA, and the magnitude of VA is given by this. VA will be 2 divided by root 3 V star sine of pi by 3 minus alpha. Similarly, you can resolve this V star along VB, and magnitude is given at 2 root 3 V star into sine of alpha. Whereas magnitude of V1 will be equal to input voltage to the inverter, that will be equal to VDC. V2 will be also equal to a VDC. And once you get the VA, VB, from that we can get the VA is known, V1 is known, TC is known, 1 upon Fs will be a switching frequency is known. So TS will be 1 upon Fs, and TS by 2 is the TC. So we know the TC, we know the VA, we know the V1, we get TA. Similarly, we know the VB, V2, and TC, we get TB. TA plus TB plus T0 will be equal to TC, and from that we'll get 3 times. Last time we discussed how to get TA, TB, and TC. And then we have to apply this. So we find out the times. This is the first step is the V0. So T0 period, we are having T0 is for V7 or V0. So we T0 by 2 period, we apply V0. T0 by 2 period, we apply V7. So we start at T0 by 2 period, we apply the V0. V0 means this is switching signal for, last time we have discussed, the switching signal for, we are getting, this will be for S1. This will be a second signal will be S3, and this will be S5. And inverted will be lower up switch. So inverted of this will be for S4. Inverted of second will be a S3, S6, and inverted of S5 will be the S2. So these are switching signals we are getting for 3 upper devices. And so here, so we apply T0 by 2 period. V0 means upper devices are off, 0, 0, 0. Lower devices are on. So we are considering S1 is off, S4 is on, S6 is on, so S3 is off. And here S2 is on, so here S5 is off. V1 is 1, 0, 0. Okay, so upper S1 is on, lower S6 is on, and then S2 is on, so S5 is off. So this is a V1. Then we apply the V2. V7 means all upper 3 devices are on here. Again we can apply V7. Then we apply V2 for a period of TA, and TB, and V1 for a period of TA and T0. So we make a symmetry at the center of this. And at one instant from TA to TB, there will be only one switching. So one device will turn off and one device will turn on. So this will be a switching signal for S1, S3, S5 for a very short duration, TS. The next duration, depending upon the alpha values, alpha is changing continuously here. Alpha is changing continuously. And depending upon that, time period will change, and you will get the change in the TA, TB, and T0. Now, whenever space vector is in sector 4, let us say 1, 2, 3, 4. If it is in the 4, which signals we can apply? We can apply V4, we can apply V5, and then we can apply V0 and V7. What sequence we can apply? We apply sequence such a way that there will be only one change of the switch. One will be turn off and one will be turn on. This is the output voltage waveform. This is the line voltage waveform. Okay, where you see the positive half cycle of voltage. This will show the negative half cycle of voltage. And here we have shown it here. This is our phase voltage. Sorry, phase current we are having. And this is the line voltage. This is the phase current and the line voltage. And we have seen that particularly line voltage is leading the phase current. So, and our phase current is almost the sinusoid one. Now we have to compare this with 180 degrees mode of conduction. So we make a comparison of space vector PWM with 180 degrees mode of conduction. And for that, so this is the waveform you are knowing. This is the line voltage waveform of 180 degrees mode of conduction, or this is the line voltage waveform of a square wave inverter or the 6-step inverter. Three names: square wave inverter, 180 degrees mode of conduction, and a 6-step inverter. All are one and same. And line voltage waveform VAB, 120 degrees plus VDC, 60 degrees 0, again 120 degrees minus VDC, 60 degrees 0, and this. And we have done already so many times, we have made this, and we have seen that this will be peak amplitude of fundamental. It will get it a root 2 root 3 by pi VDC. That will be a peak amplitude. And we have shown it here. We find out the expression for AN. Can you recall? We have done the expression for AN. Okay, I am not going to repeat once again. You are knowing what is the expression for AN. What is meaning of AN? AN will be a peak amplitude of nth harmonic. That we are already having the expression. We used it, and with that we are getting the peak amplitude of fundamental. This is the peak amplitude of fundamental, 2 into square root 3 by pi VDC. And we have shown it also. It contains the harmonics 6m plus 1 and 6 minus m. We find the THD of this waveform. Already we have done this, and the THD is a 30.4%. How we compare with now here for 180 RMF, particularly for 180 degrees mode of conduction, the RMS value, particularly for this waveform, our RMS value is square root 2 by 3 VDC. Square mean root. So square root 2 by 3 VDC is the RMS value of line voltage, and to 0.816 VDC. And our fundamental component of line voltage, this is the peak amplitude divided by peak amplitude line voltage. Okay, peak amplitude of line voltage, and we can divide it by root 2, fundamental component of line voltage. So to this, it is a peak amplitude divided by root 2. So it will be root 6 by pi into VDC, root 6 by pi into VDC. That will be a fundamental component of line voltage, RMS line voltage, or fundamental component of RMS line voltage, and this will be equal to 0.708 VDC. Now we have to, this is our, okay, we have shown the maximum possible space vector, where we can get the linear range. What is mean linear range? Where output is directly proportional to M, you can call it. Where output is directly proportional to M, that we can call as linear range, and it will be a space vector is a inscribing circle. Okay, space vector is the inscribing circle, and it will, you can find out the magnitude of this. What is the relationship between V star and VDC? So here, the relationship between V star and VDC. So this angle is how much? This angle will be a 30 degrees. Okay, and you can see that our V star will be equal to how much? V star will be equal to how much we can get it? VDC cos 30. Okay, we get the VDC multiplied by a cos of 30. Cos of 30. So you will get the maximum magnitude of V star, that will be VDC cos of 30, maximum voltage. And this V star is nothing but, what is the relationship between V star and the phase voltage? V star and phase voltage is V star or V space vector will be equal to 3 by 2 into Vm. What is meaning of Vm here? What is meaning of Vm? V star will be a 3 by 2 Vm. And anybody can tell what is the meaning of Vm? Relationship between, we are getting the space vector and the voltage. We are done at the time of defining the voltage space vector. Okay, so if you go for that slide, quickly we can go to that slide. So this is what we are having, a relationship between this V star and this will be what we are having. So what is that VM here?
Maximum line voltage.
Peak value of line voltage. Is it right? So our V star will be, sorry, VM will be peak amplitude of a phase voltage, and V star will be the magnitude of the space vector. And here we get the V star. V star will be VDC cos 30. And from that, we find out the what is the VM possible. So this analysis we have done it here. This will be a relationship. First, we have discussed that V star is the maximum space vector amplitude in the linear region. This is the maximum amplitude in the linear region. Okay, inscribing circle you can call that will be a maximum range. Relationship between VM. VM is what? Peak amplitude of phase voltage and the space vector magnitude. Here V star will be our space vector magnitude. Our V star will be 3 by 2 VM. Or here we are written VM will be 2 by 3 V star. And now here V star we find out in terms of VDC, and V star will be a V1 cos of 30 degrees. And V1 is nothing but VDC. So cos 30 is 0.866. So what we get, VM will be equal to, that is peak value of phase voltage will be equal to 0.866 VDC. And now once we get the VM, so this will be our, sorry, here you, okay, you can have a separate. So V star will be V1 cos 30, and that V star will be V1 cos 30 will, so V star will be 0.86 VDC. And VM will be, V peak will be a 2 by 3 V star. So this will be our V star magnitude, V1 cos 30. Okay. So this V1 cos 30 will be a 2 by 3 we have taken as it is, and V star will be 0.86. So peak value of phase voltage in terms of VDC will be equal to, this will be 0.577, that will be a peak. And it's 0.577 divided by root 2, that will be equal to VPH RMS. This will be a RMS phase voltage. And this RMS phase voltage is 0.408 VDC. You multiply it by root 3 to get the RMS value of line voltage. This is RMS value of fundamental component of line voltage. And now we take the ratio. So how much is voltage possible with 6 step? That in case of 6 step, this is a RMS value of line voltage. RMS value of the fundamental component line voltage is 0.78 VDC we can obtain in case of 6 step inverter. Whereas in case of this space vector PWM, we obtain 0.7066 VDC. And if you take the ratio output with the space vector PWM to output with 6 step, and that ratio will comes out to be a 0.905. So space vector PWM will give the output that is 0.905 times of a square wave. So space vector gives 90.5% of the 6 step VSI in the linear region. So that is the one drawback. Which technique will give a highest output voltage? Which technique will give the highest voltage, highest output voltage? Which technique will give the highest output voltage? Am I audible? I am okay working with mobile range. Hello?
Yes, sir.
Yes, sir, audible.
Yes, okay. So here, which inverter, which technique of two-level inverter will give the maximum voltage? Which switching technique will give the maximum output voltage? And that technique is 180 degrees mode of conduction will give the maximum voltage. And with comparison to that, our space vector will give how much? 90.5%. Space vector will give the 90.5% of that of the 6 step. So is it clear? So we just compare space vector PWM with 6 step inverter, or you can call as space vector PWM with 180 degrees mode of conduction. Any question? Now there is a numerical problem. You try, it is a just substitution problem. So we are giving a 3-phase bridge inverter. It is supplied from 600 volts. So our bridge inverter two-level inverter. VDC is how much now? VDC will be a 600 volt. VDC is of 600 volt. And what is the magnitude of space vector? Space vector magnitude is 325. This space vector magnitude is 320, and it makes an angle alpha here given. Alpha is a 20 degrees. Alpha we are given is a 20 degrees. And now the V1 is how much? What is the magnitude of V1 here? Anybody? What is the magnitude of V1? V1 is the switching vector of two-level inverter 100. S1 switches on are S1. Then next is S6 and S2. So what should be the V1? What should be magnitude of V1? Our DC supply voltage is 600 volt given to the inverter. Then what should be value of V1?
563.8.
Hello?
VDC cost.
V1 will be equal to VDC.
Cost.
Okay. You have just understood that V1 will be equal to how much? VDC. You have just gone. Okay, you can just go back. V1 will be equal to, so whatever here we are having. This V1 will be equal to VDC, where we have shown it here. Just a minute. So this whatever V1, V2, all this magnitude will be equal to VDC. So it is okay. You see the space vector, that is V1 or VDC. It will be equal to the VDC. So V1 will be equal to how much?
600.
V1 will be equal to VDC. Okay, and alpha is 20 degrees. Switching frequency is 10 kilohertz. So you get Fs, and then you get Ts. Ts is the cycle time. What is Ts? Ts will be equal to 1 upon Fs. Ts will be equal to 1 upon Fs. And once we get the Ts, how we get Tc? Anybody? How is the formula for Tc? Ts is divided into two equal parts. If you go back, Ts is divided into two equal parts. Okay, this Ts is divided into two equal parts, and that is the Tc. One part is the Tc, another. So here, what is the value of Tc now? Tc will be Ts by 2. Is it clear? Tc is a Ts by 2. So now we are getting almost all values. Is it right? We are knowing what is V1. We are knowing what is a Tc. And then we have to calculate Ta, Tb and Tg. We have to calculate first Va. Okay. V star we resolve along V1. That will be Va. Already we have, it is a sector 1. So whatever the direct substitution is there. Okay. So we are having this particular here. So we get the Va. So this is a V star resolve along V1. Va is there. V star is how much now magnitude? Already magnitude is given. V star. V star is 325. That magnitude is given. V star in the problem is given. Okay, 325. So we are having a V star is given. V star is given. Alpha is given. Alpha is given. Then we can find out the Va. Similarly, we can find out the Vb. Okay, we can find out the Vb. Vb will be 2 by root 3 V star sin alpha. You will get the Vb. Okay, once you get the Va, Vb, then we have to, V1 is known. Already V1, V2 is known. V1 is how much? VDC. Okay, V2 is also VDC. Va and Vb you calculate. You have calculated the Tc. And once you calculated this, you can find out the Ta and Tb. Once Ta and Tb is known, you can find out the T0. So this is just a substitution, and you can correspondingly you make a switching signal for one cycle time. Okay, one switching cycle time. So this is all about our. So any question? How to solve the problem? It is a sector 1. So we have to apply V1, we have to apply V2, we have to apply V0 and V7. What are steps? You have to determine Va and Vb, determine magnitude of V1, determine Tc, use the expressions for Ta, Tb and T0. So is it clear? Any doubts? Hello? any question regarding this numerical problem? So you should know the expression for VA, you should know the expression for VB, you should know the magnitude of V1, and you know the TS. Our switching frequency is given 10 kilohertz. From that you find out TS. TS by 2 will be a TC. Just it is a substitution problem. You can just find out the answer for this. So any question? Hello?
No, sir.
Am I audible?
No, sir.
Yes, okay. Then let us go
Yes,
for
sir, audible.
our next. What is mean by the multi-level inverter? So today we just make the introduction to this. What is mean by the multi-level inverter? So we are having some of the drives, multi-megawatt drives, induction motor drives, which are fed from inverter. So what should be the? It will be a 3.3 kV or 6.6 kV. That is voltage rating of the particular this induction motor. We are using a medium voltage. This is called as medium voltage. Our 400 volts is what we can call it as a low voltage. 3.3 kV or 6.6 kV. This voltage we can call as a medium voltage. And our rating of the motor, a particular maybe a 2 megawatt. Let us know that 2 megawatt. Our rating of the motor is the 2 megawatt. And what is the current will voltage rating will be 3.3 kV or 6.6 kV, and power rating is 2 megawatt. And from that you find out, calculate the current, root 3 VLIL cos pi. Okay, root 3 VLIL cos pi. Now what is formula we have to use? Root 3 VL line voltage, IL line current, and then cos pi, a power factor of the motor. You can assume it as a 0.9 maximum, let us. And from that cos pi is known. This will be equal to 2 megawatt MW output power. 2 megawatt will be root 3 VLIL cos pi. Already VL you are knowing, maybe a 3.3 or 6.6 kV. Cos pi is 0.9, you assume it 2 megawatt. And you find out the current. And this current will become as few kiloamperes, maybe 1 kiloampere, 2 kiloampere, something like that. Okay. And now particularly for this, we are, let us take a very specific, we are having a 6.6 kV and 2 megawatt, 6.6 kV motor. Okay, 6.6 kV, 2 megawatt motor. And now we want to have a 2-level inverter. This is the inverter we have shown. This inverter is a 2-level inverter. We have discussed what is meant by the 2-level inverter. It has having a VAO, a pole voltage we have given. It is a plus VDC by 2 minus, or a conventional bridge inverter you can call as a 2-level inverter. Now how much voltage we have to hear? This motor voltage is how much? Motor voltage is a 6.6 kV. A line voltage is a 6.6 kV. Is it right? This will be a, let us assume that this will be a 6.6 kV. Okay, that is a voltage. Then how much VDC is required for 6.6 kV? VDC, how much is the VDC is required for 6.6 kV? And we have just shown it here. So here we have seen it here. What is the relationship between the VL RMS and the VDC? This is a, okay, we are having a space vector PWM. If we use it, our VL RMS here we are having is how much? 6.6 kV. VL RMS is how much? VL RMS is 6.6 kV. And based on that, our VL RMS equal to 0.7066 VDC. So here, water voltage, we are having 6.6 kV. We have to divide by 0.7. And that will be our VDC. So 6.6 kV divided by 0.7, you find out. Maybe, okay, let us assume that 8.5 kV. We'll assume it, okay, just find out, calculate it. So let us go for, this will be 8.5 kV. This will be 8.5 kV. So how much is the DC link voltage required? Let us assume, may not be exact figure. So this is 6.6 divided by 0.7. Let us assume that this figure comes out to be a 8.5 kV. So how much should be the voltage rating of our IGBT? If DC link voltage is a 8.5 kV, what should the voltage rating of the IGBT? Anybody? How much voltage should appear? Suppose S1 is on, how much voltage should appear across the S4? Or when S4 is on, how much voltage will appear across S1? Hello? Am I audible? Here, for getting a 6.6 kV line voltage, RMS value of line voltage fundamental component, we assume that the rating required is 6.6 divided by 0.7. So we assume that figure is 8.5 kV. May not be correct, but you assume it is 8.5 kV. Then how much voltage will appear across the switch when it is off? How much voltage will appear across S1 when it is off or S4 when it is off? How much? It will be
8.5.
equal to how much? 8 kV will appear. And normal trend is if 8.5 kV voltage is appearing, then what should be the voltage rating of device? Our voltage rating of device is roughly 2 times of its whatever voltage appearing across it. 2 times whatever voltage appearing across it. So here we are having a 8.5 kV is a voltage appearing across the S1 or any switch. Then what should be voltage rating of the device? It is 2 times. So almost 17 kV voltage rating. So here we can say that the voltage rating required is how much? For a 6.6 kV drive, we require a 17 kV voltage rating. Means our single device, what should be voltage rating? For a device rating, voltage rating will be a 17 kV. Okay, so our one switch should be able to withstand this much of this. And then we have seen that we can't have the device of that much voltage rating. IGBT, we can't have a voltage rating of 17 kV. It may be a 5 kV or 4 kV or 3 kV, 6 kV maximum. May not be a 17 kV. It will be difficult. Then how to solve the problem? Is it right? We are using a 2-level inverter for very big motor, 2 megawatt motor, and its rating is 6.6 kV. And when your motor rating is 6.6 kV, how much should be the device voltage rating? Device voltage rating required, one IGBT voltage rating is 17 kV, whereas current rating may be 1 kilo ampere. And getting this device is a very difficult job. Then what is our solution? We can go for another inverter topology, and that is what we can call as a multi-level inverter. What we can call as a multi-level inverter. And if it is 5 level is there, so we are using our voltage across each device will be reduced by level -1. So here 17 kV, if it is 5 level multi-level inverter, so let us go for 5 level. So here what is the voltage rating of one device? Then one device rating will be a for 5 level, whatever the 17 kV divided by 4. 17 kV divided by 4. So we get around 4.25, something like that. So 4 kilo ampere, 4 kV, sorry, 4 kV will be a voltage rating. That can be. So now in your case, when you use a 5 level multi-level inverter, we are not doing what is multi-level, but when we use a multi-level inverter, then the voltage rating of the device required will be reduced. We are going to discuss, okay, advantages of multi-level inverter after introduction of multi-level inverter. So let us skip this point, advantages. And here we have shown, here we have taken an example of 6 kV. Okay, instead of 6.6 kV, we have just discussed is the 6.6, but okay, you can call a 6 kV motor. Induction motor is 1 megawatt. We have shown this particularly rating, a particular size of this motor, and the particular this may be around 7 to 8 feet total. Okay, this may be a 10 feet. Length will be 10 feet, height may be a 10 feet, something 10 by 10, something this motor we are having. And we want to find out the what should be the, we are supplied with a 2-level inverter. And then what should be the DC link voltage with a space vector PWM. And VLRMS, we have just gone it here. 0.7066 VDC. VLRMS is 6 kV, and from that putting this VLRMS will be equal to 6 kV. Putting this, we'll get the VDC, and now the VDC will be a 4.5 kV. Sorry, 8.5 kV. VDC will be a 8.5 kV. And now what should be device rating? Roughly we are taking the 2 times of that. So a 17 kV. But single device is not possible. And if you use a 5-level inverter, I just told, without telling what is a multi-level inverter, our device rating will reduce. So one of the objective of use the multi-level inverter is we can use the lower voltage rating devices. In case of multi-level inverter, voltage rating of the device is less as compared to a 2-level inverter. Now, okay, advantages. Okay, we'll just go after this. What is meant by multi-level inverter? Okay, so how we classify this? Okay, multi-level inverters will be depending upon the number of pole voltage levels. Classification is one is a number of pole voltage levels. So if you see it here, this is a particularly we have shown it a switch here. It is nothing but the one leg of inverter. It is a one leg of the inverter, and this particular we have shown 2-level inverter. What is our one leg? In case of 2-level inverter, okay, one leg we can show it here. Okay, so okay, I'll show the devices like this. This is the one leg of the inverter. Okay, anti-parallel diode is there, and this is our A point. Okay, what we are having is the A point, and across this we are having a VDC. Across these points we are having VDC. So here A point is connected to either upper side of this or lower side of this. Okay, so we are having only just. So here this one leg is having the 2 devices, and this is represented as a one leg where 2 possible. The S1 is on. Let us assume that this is our device number 1, S1, switch is upper. Lower we are having the switch S4 is on. So if you see this will be a representing, this is a O point we have generated, center point. So center point is our center of the DC link, this point, and this switch is nothing but a one leg of the particular inverter. When upper switch is on, let us assume that switch is close to the upper. So what will be VA of this O point and this O point is the same. So VO will be plus VDC by 2. When upper switch is closed or when switch is this position, we'll get a plus VDC by 2. Whenever switch is lower switch is closed, we'll get a minus VDC by 2. So here a pole voltage levels. Here we are having a pole voltage levels are plus VDC by 2 or minus VDC by 2. These two, then that is why it is called as a 2-level. Now if you see here, what is meant by the 3-level? So we are getting the pole voltage here. A pole voltage is our VAO. Let us assume that VAO, a pole voltage here. And what are the possible values here? When the switch is close to the upper, here we have seen that it will be a plus VDC by 2. Plus VDC by 2. That is one level. When the switch is in the second position, we'll get a VAO will be equal to 0. Second will be 0. Okay, both A and O are shorted. And third is VAO will be equal to a minus VDC by 2. With respect to O, our voltage VAO will be minus VDC by 2. So here pole voltage is having how many levels? Here pole voltage is having 3 levels. What are these 3 levels? Pole voltage is having 3 levels. So it will be equal to VAO plus VDC by 2, minus VDC by 2 and 0. We are having a plus VDC by 2, minus VDC by 2, 0. 3 levels. And these 3 switchings we can obtain with the help of number of IGBTs. Here for this we require maybe how many 4 IGBTs are required per leg, that will going to discuss. Okay, so here why we are calling 3 level, because we are getting this VAO, A with respect to O, we are having a 3 distinct values, that is plus VDC by 2, 0 and minus VDC by 2. Similarly, here we have shown it 5 level. Okay, this center point O here connected. So here what we get, each is a VDC by 4. So with respect to this, when is a plus VDC by 2, plus VDC by 4. So what are the levels here we get? In case of this circuit, if you see here, what levels with respect to this point O, this VDC by 4 and VDC by 4. So upper is that. So one is plus VDC by 2. That will be a one level is a plus VDC by 2. Okay. A second level is just one switch here. So it is a plus VDC by 4. Okay, VDC by 4 plus VDC by 4. Okay. And now third, if our this A point O point 0. Here case, so when switch is there, so this capacitor will come across, that is a minus VDC by 4, minus VDC by 4. Okay, and then whenever point this A is here, we have seen that two capacitors, so minus VDC by VDC by 2. So these are the 5 levels we'll get. Pole voltage has 5 levels, and these, what are these 5 voltage levels? So when A is connected to upper, two capacitors voltage V plus VDC by 2, it is shown position, one capacitor VDC by 4. It is O and A are shorted, so 0. Again, whenever A is coming to this position, it will be minus VDC by 4, and whenever A is with this position, minus VDC by 2. So it is having a 5 pole voltage levels, and that will be a plus VDC by 2, plus VDC by 4, 0, minus VDC by 4, and minus VDC by 2. So whether it is a 2 level, 3 level, 4 level, 5 level, that depends upon what are the pole voltage levels. So here whatever we discuss, we have shown it here. So this is particularly a 2 level. What we discuss, we are, if we just consider first here lower part, pole voltage. You consider this part what we discussed here just now. A 2 level, we get the 2 levels plus VDC by 2 and minus VDC by 2. For this is a plus VDC by 2 and minus VDC by 2. This is what 3 level. If you just minus VDC by 2, 0 plus VDC by 2, minus VDC by 2, 0 plus VDC by 2. And the 5 level, minus VDC by 4, minus VDC by 2, 0 plus VDC by 4 and plus VDC by 2. So that will be the levels we obtain. Now here we have taken the reference point as a center of these. Now another possible option is you can measure the voltage not from the center of this. You can take a negative side of this. This is you can take as a center here. This is you can take a center here. If you take the lower line as the reference here, not the center of DC link, and with respect to this X point, let us assume that with respect to X, if you measure the voltage, here voltage levels will be a lower side 0 and VDC. So here levels, in case of 2 level, it will be 0 and VDC. Is it clear? In case of 2 level, the voltage levels will be, when the lower side it is connected, it will 0 and VDC. So if you go for this, a 2 level, it will be a 0 and the VDC. If you go for here, what we are having? Here, in case of 3 level, it will be a VDC total voltage with respect to this X point we are measuring. So this is a VDC upper connected plus VDC. Then when it is connected to this side, VDC by 2, and when it is connected to lower side, it will be 0. So here VDC we are getting first case VDC, second is VDC by 2, and third is 0. So these 3 levels. So in this case, if you lower reference point, so 0, VDC by 2 and VDC. Then in case of 5 level, okay, in case of 5 level, so you will get a plus VDC. Okay, so you can just have a plus VDC, then plus VDC by 4. So here if you go for this side, plus VDC by 4, then here VDC by 2, then 3/4 VDC and the VDC. So this will be our what we are getting the 5 levels. So anyway you can call it, but we'll prefer the second method, pole voltages with the center of DC supply. So it will be whatever our discussion. We can take this for our, okay, henceforth we'll discuss. This is also possible. Some papers are referring this, but we will stick to the lower one. We will stick to the this particular. So is it how we define this number of levels? That will be depending upon the pole voltage levels. 2 level, 3 level, 5 level, 7 level, 9 level. We can have many number of levels. Okay, and now let us, this is one classification. Another classification is based on circuit diagram. Another classification is based on the circuit diagram, and that classification you can call as a topologies. That will be based on the circuit configuration. And we are having three types of these multi-level inverters. One is a neutral point clamped, NPC, or diode clamped multi-level inverter. This is a circuit-based circuit, various circuit configuration. So first is neutral point clamped, NPC, or diode clamped multi-level inverter. Then next is flying capacitor multi-level inverter. And third is cascaded H bridge multi-level inverter. So classification of inverter based on circuit configurations, three types: neutral point clamped or diode clamped multi-level inverter, flying capacitor multi-level inverter, and cascaded H bridge multi-level inverter. And now we are going for one circuit configuration. Now we start with diode clamped or the neutral point clamp multi-level inverter. So this is our circuit configuration. So we'll discuss the circuit configuration of this. So this is our DC supply. We want to split the DC supply into two equal parts. We are having a single DC supply. We have a single DC supply. We want to split the DC supply into VDC by 2, VDC by 2. What arrangement you can suggest? If I want to split up the DC supply into two equal parts, VDC by 2, VDC by 2, what should be one of the possible option? What should be one of the possible option? So we have to use the two capacitors. Okay, we have to use the two capacitors. So here we use the capacitor to split the DC link voltage. Our DC link voltage is VDC, and that we want to split up into half of that. So VDC by 2, VDC by 2. So we use the two capacitors of equal size, and this center point of these connection points of these two capacitors will be the 0 point or O point, we can call it. O point we can call it. And now if you look at this, we are having three legs. We are having a particularly three legs, and each leg is having how many devices? Each leg we are having a 4 devices. So here a first leg is having 4 devices, second leg is having 4 devices, and third leg is also having the 4 devices. And we use the diode to clamp the voltage. Here we have shown it, we are used the diode here. Okay, diodes are used. And this O point, center point, is connected at the diodes, and output will be conventionally we take at points from A, B, C. That will be this. So this circuit configuration particularly we can call as a 3 level. What levels we get it here? In case of 3 levels, in terms of center point, let us assume that what levels of this VAO we can obtain here. What in case of 3 level, what will be our VAO? One is plus VDC by 2. Output VO is plus VDC by 2. What is second is 0. And third is minus VDC by 2. So these 3 levels we obtain with respect to O point. This is our O point, and the A. This is the output of A. Similarly here O, and this is the B. And similarly from O, and this is the C. So VAO, VBO, VCO. In case of this 3 level inverter, What is our VAO, VBO, VCO? So here I'll just write VAO will how much? VAO will be either these three values, plus VDC by 2, 0, minus VDC by 2. What is VBO? VBO will be again plus VDC by 2, 0, minus VDC by 2. VBO. VBO. And then similarly we are having VCO. Again VCO we are having this. Is it clear? So in case of two level, we are having VBO, VCO, VAO only plus VDC by 2 or minus VDC by 2. But in three level, we are getting one additional voltage level for this three level. That will be VAO will be 0, or VBO will be 0, or VCO will be a 0. So these are three levels. Now once we obtain these three levels, the space vector diagram, obtaining space vector diagram is same as that of two level inverter. Drawing the space vector diagram is similar to that of two level inverter. First, from VAO, VBO, VCO, what we can do? From VAO, VBO, VCO, we can find out phase voltages VAN, VBN, VCN. And once you know this process is the same. Okay, once you get three different values, but our process of finding out the switching states or the space vector is the same. What is the procedure? Procedure is same what we have done it here. This is the procedure. Procedure is same. Here VAO, VBO, CO, that values will be different. Okay, we are going to study tomorrow. What is VAO has three values, plus VDC by 2, minus VDC by 2, 0. Similarly, VBO has three different values. VCO will have three different values. Once you know this, any value, maybe VO 0, VBO maybe plus, depending, so many combinations are possible. And once you know these specific levels of VAO, VBO, so we find out VAN, VBN, VCN using this matrix. Once we know the VAN, VBN, CN, once we know this VAN, VBN, CN, we can find out the VX and VY. And once we find out Vx and Vy, we can find out the switching space vector. So the process, what I want to trace is the particularly this VAO, VBO, VCO has only three specific values. And once you know the VAO, VBO, VCO, you can find out the switching. We can define how to make the switching. In case of our two-level inverter, we are calling as 1, 0, 0. We are using 0 means lower switch on, 1 means upper switch on. Here you can, instead of that, we can use A, B, and O. Okay, we can use A, B, O symbols. We can discuss this switching. We can represent with this ABO. In case of two level, how we represented the switching of the switches? 1 means upper switch on, 0 means lower switch on. Okay, that logic we have made it here, particularly one leg, and here this one leg, one device is on, other leg. So now, so what are this particularly this how we get the switching states of this, and how we get these voltage levels plus VDC by 2, minus VDC by 2, and 0, that we discuss next time. So this is the just we started with the multi-level inverter, and one advantage of multi-level inverter we just discussed. What is that advantage of multi-level inverter? What will be the advantage of multi-level inverter? Anybody can unmute and tell.
Less voltage across any device.
So we use a less voltage rating device for higher voltage rating application. Our 6.6 kV motor or 6 kV motor, we can use a 4.5 kV device. Otherwise, if you want to use a two-level inverter, for that we have to use the device of 17 kV voltage rating. That may not be feasible, and that is why, so device used, we can go for a multi-level inverter for high voltage application, where we can use a lower voltage rating of the devices which are available. Okay. Other advantages we will discuss after getting introduction to various topologies of that, and we have discussed the classification based on two things. One is number of levels, and what is level we have discussed. What is mean by 2 level, what is 3 level, 5 level, and how to get it. Two conventions are there. One is with respect to center point of DC. Another is from the negative rail of the DC. Based on that, so pole voltages, this is from the negative reference with a negative rail of the DC supply, and this is a based on the center point of DC supply, and we will we will take particularly the center point of the DC supply, particularly for this configuration what we have just studied. So tomorrow we'll concentrate on the neutral point clamp multi-level inverter. So any questions? Hello?
No, sir.
Okay, so we'll meet tomorrow at 10:15. Thank you. Send me the recording. Is it right? Huh?